All right, so we're back on. Where were we? Oh, so we drew circles showing that both the hydrogen and the chlorine were more stable. Now, we're done, right? No. Why not?
Polar covalent.
Oh, well, yeah, we're going to get to the polar stuff, too. Yeah, it's a polar covalent bond. But unfortunately, well, maybe fortunately, are there many compounds that have more than 2 atoms?
Yes. Like the polyatomic.
Yeah, most of them have more than 2 atoms. So we've got to figure out how to do this for things with multiple atoms. Right? Now, this is one of those cases where you don't want to get creative. Right? You want to follow steps, and at the very end, you can get a little creative. Right? But for the first few steps on this, don't create your own method. Follow the steps in the procedure. Here are the rules up here on the board, and these are on your sheets. So we're first going to do methane, CH4. So Anthony, would you nice and loudly read step number 1?
Okay. Decide which atoms are bonded to each other. Many times the central atom in a molecule is the first atom in the formula.
Okay. And that's going to happen most often. So we have carbon that we'll put in the middle, and then the hydrogens are going to go around it somewhere like that. Okay? All right, Quan, will you read the second one?
Determine the total number of valence electrons from for the atoms involved. If you are doing the dot diagram for an ion, make an adjustment to the total number of valence electrons you have just determined. If
Okay. That's good for now. So we'll see one of those hopefully before the end of the period. So if we look at carbon, how many valence electrons for carbon? We had 4 valence electrons. The 4 hydrogens would be 4 times 1 valence electron each, right? So we have a total of 8 electrons to work with. Okay, we good? All right, Jalen, can you do number 3, please?
Put a pair of electrons in your diagram for each bond. Try to forward.
No, that's it. Right. At the very least, we know that we want to bond these things together. So we need to have at least a pair of electrons to use for each of those bonds. I'm going to go ahead and do that. All right, number 4, Missy?
Complete the octets of the atoms connected to the central atom by adding pairs of electrons. Remember, however, that the element hydrogen can have a maximum of only 2 electrons.
Very good, thank you. Now, this is what I call the good host rule. So your central atom is like the host. Right? The central atom is going to make sure that the other atoms are happy first. Right? Meaning they have a stable octet, or in the case of hydrogen, just the 2. So are all the hydrogens happy? Yeah, they are. All right, so we're good there. All right, so we don't have to do that. And step number 4, 5.
Do a count of the electrons you have in place. If you have any electrons left over from your total number of valence electrons, place these electrons on the central atoms in pairs. If the central atom have fewer electrons than others, then it will be necessary to consider the possibility of multiple, double, triple bonds in your diagram.
Very good, thank you. Rule number 5 you have to be very careful with. So do we have any electrons left over? No, so we really don't have much to do. Does the central atom have fewer than an octet? No, it's got an octet. It's got 8 around it. If I drew a circle around the carbon, we would see that it has 8 electrons around it. So the carbon is happy, right? So we don't need to think about double or triple bonds here. So we're done. Right? We've satisfied all the steps in the thing, and that would be our dot structure for methane. Good enough? All right, so let's try water. Oh, where do we leave off? All right, Missy. Sorry, Tess. Tess, what am I going to do first?
Determine what atoms are bonded to each other.
Good. So this is one of those cases where, what?
Well, they're, it's different nonmetals.
No, forget about that. These are all for covalent substances.
Okay.
This is one of the cases, though, where what? What does rule number 1 say?
Well, the central atom was not.
Yeah, exactly. The central atom's not first here. We know that water is going to have oxygen in the middle. Okay. Just a general rule of thumb: hydrogen never going to be your central atom. Right? Never. Okay. How many electrons for oxygen? 6 valence electrons. Hydrogen. Right. So 2 times 1 valence electron each. Total of 8 electrons. So Bianca, what am I going to do next?
So
Your rules. We left off on. No, okay, yep, we did that. Right. We know we have to have pairs for the bonds. So we're going to put those in first because we know they have to be there. Right. And then what comes next? Jalen? Good. The good host rule. Oxygen looks out. Are the hydrogens happy? Yeah, then we don't need to do anything. Okay. Now, rule number 5. What do we do, Missy?
How many electrons do you have?
Yep. So there's 4 so far.
We need 8.
Well, no. What do we read? Rule number 5. Is it 5 we're talking about? Yeah, 5.
Do you count of the electrons you have placed? If you have any left over from your total number of valence electrons, place these electrons on the central atom.
Good. Now, one of the things I like to do, and these are just for the lone pair, the pairs that are on the central atom, is I like to draw circles around them just to remind myself that they're there. All right. These are called lone pairs. And these are called bonding pairs. All right, and then the last part of this one is, does the central atom have fewer than an octet? No, it doesn't. So we're all good, right? So we're done with the dot structure for water. All right, I think we need to do one on our own. All right, so SiS2. So what I'd like you to do is do this one on your own and see how far you can get before you kind of feel like you're stumped and you need to talk to the person next to you. All right, see how far you can get on SiS2. So these guys are working on this, and we got silicon, sulfur, sulfur. Silicon has 4 valence electrons. The 2 sulfurs will add 2 times 6 valence electrons. So that gives us a total of 16 electrons to work with. And so we put a pair in for each bond. We do the good host thing. Okay. And at this point, most of them are a little stuck.
It's like this.
Huh?
I think
No, this can't be right, because why?
Because silicon's not happy.
Yeah, silicon's not happy right now. So I've gotten up through step number 4, but now I've used up all my electrons. Again, follow the steps. Do I have any electrons left over? No, so I can't put any more on the central atom. Do I have fewer than an octet? Yes. So then I must consider double bonds, right? Now, what's a double bond? Well, yeah, instead of just sharing 1 pair of electrons, you share 2 pairs. So we'll take a pair off of this sulfur and put it there. Okay, now notice by doing that, we don't take electrons away from sulfur, we just add them to the silicon. Now, in some sense, we do take them away, because before there were sulfurs all by itself, like sulfur had them, right? Sulfur had them all by himself. But now sulfur's got to share them with the silicon, and that gets us partway there, but then we need to do it the other side too. So now we look at this sulfur is happy, this sulfur is happy, and the silicon is happy. All right, now, what we want to do now is think just for a minute about this. If we look at this bond here, right, now the sophisticated way to think about this is instead of 2 electrons worth of density, we now have 4 electrons worth of density. So we have 2 pairs or 4 electrons worth of density. Now we call that as a double bond. Now what do you suppose the implications of that are going to be? If we put 4 electrons worth of density in there holding the atoms together, what do you suppose happens? Good. We get a stronger bond. And one other very important thing that seems a little less obvious. What's going to happen to the distance between the atoms? So that's the tricky part, right? You're putting more electron density there, so you'd think there should be more space. Yeah, no. Right, did you hear that? That was Quan. No. Right? Instead, by putting more electron density, you're actually going to pull the nuclei closer together. So the bond length will be shorter. Right, so when you make a double bond, the bond length will be shorter than what a single bond would be between the same 2 elements, or atoms of the same 2 elements. All right, pretty good. Pretty good. That's not too bad. All right, next one. Let's give this one a shot. SF4. Again, just follow your rules carefully, and it should guide you through doing this one. So we've had a little bit of time to think about this. We're going to put sulfur, the fluorines around it. You know, so far we're looking pretty familiar. Yeah, not too different. Sulfur, 6 valence electrons. Oh my gosh. 4 times the fluorine. So 34 total electrons to work with. A lot more electrons, right? So we put a pair in for each bond. Right, that's going to hold them all together. Good host rule. Right, we're following the rules. Okay, so we put all the electrons in place. We did the good host rule, made them stable. Now we do a count of the electrons. Are there any left over?
Yes.
Yes, 2. The rules are very specific. What do you do with those 2 electrons?
Place these electrons in the central atom.
Put them on the central atom in pairs. And again, it looks a little crowded there, so I'm going to put them there and I'm going to circle them just so they kind of stand out and I know that they're there. Again, this isn't, no thinking about this, just follow the rules. Okay? Now, what's the next part? Does the central atom have what? Does the central atom have
It has fewer electrons than the octet.
fewer than an octet? It doesn't say anything about having more than an octet. Right? It just says fewer than an octet. So does that have fewer than an octet? No. So we're good. This is fine. This is perfectly fine. Right? Yep.
Just put it in the corner.
Huh?
Extra term.
Yeah, the placement of things isn't really significant right now. I mean, when we start to go to the next thing, which is VSEPR, it will become more significant, but for right now, that's fine. Now, real quick before the bell rings, here's one of those ions that step number 2 talks about. Right? So if I do nitrogen has 5 valence electrons, and my 4 hydrogens gives me 4 valence electrons. So that's 9 electrons to work with, except somebody took one of my electrons. So I've got to subtract 1. So I really only have 8 electrons to work with. Right. So I'd have nitrogen, hydrogen, hydrogen, hydrogen. Of course, I'm jumping way ahead, or very quickly. You need to put a bracket around it just to make sure that you show that there's a charge on this whole thing. Right? Because otherwise somebody would look at that and think it's a molecule, but it's really an ion. Okay? All right, very good. All right, so you want to do that page, the front page of that worksheet. Yeah, just the front page, don't do the back. And then I think there's a couple in the book, too, that you have to do for homework.